Welcome to a lesson with Dr. Powell. We're going to continue the last video where we were talking about derivatives being linear transformations. Um, and we were looking at the case where we have one input and one output. And it was a function from a linear transformation from a vector space of runs to a vector space of rises. But we're going to do this in a more interesting example when we have two inputs now and one output. So that our derivative is going to be a linear transformation from a vector space of runs to a vector space of rises. Run is like change of input, rise is like change of output. Okay, and our function can be approximated as a shift of a linear transformation, a shift of the derivative linear transformation. Okay, so let's take a look at this. We have this as our function. So we have two inputs and we have one expression output. The derivative will look something like this, so two inputs and one output. This is a particular example of the derivative at a point 3, 3. So when x is 3, y is 3. And notice that our function, or a matrix that describes our linear transformation for the derivative, should take on this form, have two inputs and one output. We'll discuss how we actually got this matrix right here on the next slide. But first, let's just kind of look and see what's happening. So think change of x, change of y will induce a rise, okay? But this is assuming that we have a straight line approximation from this point to where we're rising to. And if this actually works at the point 3, 3, then we should expect this much. If we run 0.1, 0.1, so change of x 0.1, change of y 0.1 to 3.1, 3.1, we should expect that our rise to be approximately, using this approximation for rise, 1.2. Because we can plug in 0.1, 0.1 into this function, and we end up getting 0.6 plus 0.6, which is 1.2. Okay, so let's actually see how we came up with that matrix. Well, it's the same way as we usually do for any linear transformation. We just look at what the image of E1 is and what the image of E2 is. So what is E1? It means change of x is 1 and change of y is 0. That means change of y hasn't changed at all. So y is like a constant. So pretty much we're trying to see what the multiplier should be over here if we only have a single variable going in. So we just use our single variable ideas. So we just take a derivative with respect to x, assuming that y is a constant, and we just get 2x. So hence E1 will just go to the multiplier 2x here. So that's where E1 travels. And what about E2? Very similar. So change of x is not changing at all. X is not changing, so x is treated like a constant. Only y is changing, so it's the same idea. Here, if change of y is simply 1, then the output is going to be what the rise is going to be what the derivative is with respect to y. And we can kind of think about this in the following way, because the change of the function over change of y, here in this case, if we assume that f is linear, then this is actually the derivative, df dy, with respect to y, assuming that x is constant. And assuming x is constant, that's just going to be 2y. Now notice that if change of y is equal to 1, change of f is 2y. So quite literally, this really is the image, this is the rise of E2. So if E2 comes in right here, what the rise is will be 2y. So we actually get this one part at a time, and oftentimes this is thought of as taking what's called partial derivatives, meaning you pretend like only one variable is the variable and everything else is constant, and we can make that computation like that. Okay, a little notation here. We call this part right here f sub x, and here fy, you could say f partial x, f partial y if you like. This is a linear transformation. You can write it that way. And we will keep on going in the next few videos, going on this point so that we can actually talk about minimization or minimizing or maximizing a function and being able to determine if it's a minimum or a maximum. Thanks for watching.